Welcome to lecture number 23 of the course on nonlinear structural analysis, theory and applications. So, let us recall what we have done in the previous lecture. So, in the previous lecture we started reviewing the concept of pure bending for Euler-Bernoulli beam. Okay. So, subjected to pure bending, right. So, that was linear elastic, and then we stated that if we continue loading a specimen, then what will happen. So, eventually a plastic hinge will form. So, we have introduced the concept of plastic hinge, right. And then we started looking at the moment curvature response for steel cross sections. Okay. We took a very simple rectangular cross section and derived the theoretical moment curvature relationship under linear elastic and elastoplastic loading condition, assuming an elastic perfectly plastic steel material behavior, right. So, in this lecture we will continue from where we stopped in the previous lecture. So, today we will be looking at some singly symmetric section. How do we calculate the location of plastic neutral axis, the plastic section modulus, the plastic moment capacity and so on. Okay. And we will also study the different factors that can affect your moment curvature response. Okay. So, let us get started. So, this is the slide we have seen in the last lecture coming out of this book by Professor Brunet et al. Okay, ductile design of steel structures. So, we looked at this normalized moment versus normalized curvature, and we have theoretically derived the moment curvature relationship for the rectangular section, and we have also defined what is called the shape factor, which is the ratio of plastic moment to the yield moment. Okay. Remember that it is a property of the cross section. Okay. It has nothing to do with the material property, right. And as we discussed in the previous lecture, if you have more material near the web, okay, in other words, if I draw a rectangle, if I draw a wide flange section or simply I section. So, in the United States they call it wide flange section. The moment I start putting more material in the web region, then the shape factor will increase. As you can see, the diamond shape has a shape factor of 2, and for the rectangular section it is a shape factor of 1.5. Okay. And if you consider ideal wide flange section, ideal section means, as I explained in the previous lecture, you have 2 flanges, okay, there is no web, right. So, that is called an ideal wide flange section. So, for that the shape factor is equal to unity. That means, this is the linear elastic part, and then it follows basically the EPP stress strain response. Okay. So, the shape factor tells how quickly MP is reached for a given cross section. Okay. Higher the shape factor, the more curvature it takes to reach the plastic moment capacity, right. And also the shape factor dictates how much will be the spread of plasticity along the length of a beam. Okay. Higher the shape factor, higher will be the spread of plasticity. On the other hand, if you consider an ideal wide flange section, only the location of maximum bending moment that cross section will yield, there will not be any spread of plasticity for an ideal wide flange section. Okay. So, now let us talk about singly symmetric section. So, we have looked at a rectangular section which is doubly symmetric, and also some of the sections that I showed in the previous slide. So, these are all doubly symmetric, right. So, let us look at some singly symmetric section. I try to draw a shape which is rather arbitrary, but it has only one axis of symmetry, and that is this axis on which the load is being applied. Okay. So, let us say this is my plastic neutral axis, and we are trying to locate the plastic neutral axis. How do I locate? Well, I know that this section is subjected to pure bending, there is no axial force. So, if I integrate the stresses over the cross section, then what I get, integration sigma dA over the cross section must be equal to 0, right. That means, I can do this integration in 2 parts, let us say one for this one and one for that one. So, integration over A1, now this is compressive. So, negative minus sigma y dA, and this is integration over A2, this area, okay, sigma y dA is equal to 0, and that gives me A1 is equal to A2, because the stress distribution is rectangular like this. Okay. So, this tells us that the plastic neutral axis divides the cross section into two equal parts. Okay. As you can see, A1 is equal to A2, and with this definition we can locate the location of the plastic neutral axis. Now, we can calculate the plastic moment capacity. Well, that is nothing but integrating the stress distribution over this and taking the moment about the plastic neutral axis. So, integration over the area sigma into dA is the force multiplied by the lever arm y. So, now I can compute this integration in two parts. So, I can say okay, for this part the resultant is acting here. So, sigma y into this area into this distance y1 bar. So, sigma y y1 bar into A1 plus for this bottom part sigma y into A2 into y2 bar. Okay. So, this is what I get, and this is my plastic moment, which we write as Zp into sigma y, where Zp is called the plastic section modulus. Okay. So, that means from here plastic section modulus is basically your y1 bar A1 plus y2 bar A2. Okay. So, y1 bar is the centroid of this top area from the plastic neutral axis, y2 bar is the centroid of the bottom area from the plastic neutral axis. Alternatively, I can also write this y1 bar plus y2 bar into A by 2, because A1 is equal to A2, as simple as that. Okay. Now, recall when we started talking about the doubly symmetric section, we said that the plastic neutral axis and the elastic neutral axis, they coincide and pass through the centroid of the cross section, right. But for a singly symmetric section, it does not happen so. So, what happens? Let us take a look. So, let us say I have got a singly symmetric section. Here I am taking a T cross section, which is symmetric about this axis, right. Now, under elastic condition, this is the neutral axis, which I am calling Na, or you can also say ENA, elastic neutral axis, which passes through the centroid of the cross section, right. Now, as I keep applying bending moment, what will happen that this is the furthest from the neutral axis. So, here this fiber will reach the yield strength or yield stress earlier, right. So, let us say you have sigma y here under tension, so positive, and here the stress is still less than sigma y. So, no yielding, right. Now, if I continue loading it, okay, what will happen? The yielding will penetrate inside, and let us say it comes up to this point, right. At this stage, this may yield, right, and then you get a stress distribution like this, where this has shifted up. Okay. Why it is shifting up? Well, to maintain the equilibrium of forces, that axial force is not there. So, summation sigma dA integrated over the cross section must be equal to 0. That gives you, that brings the neutral axis up, and it is easy to understand when it is fully plastic. So, let us say this is another intermediate stage, and this is the fully plastic condition. So, in under fully plastic condition, this sigma y multiplied by this area must be equal to sigma y multiplied by this tension area At. So, this moves it up. If I take an example, then it will be even more clear. So, let us say I take a rectangle like that, which has a thickness T and this is B. Okay. I take the same rectangle and make the T, now it is like this. Okay. So, this is also B and this is T, right. So, you can locate the elastic neutral axis, which is going to be, let us say if this is the middle of this part, then it will be somewhere here. So, let us say this is my elastic neutral axis, right. Where is the plastic neutral axis? Well, as you can see, this area is B into T and this area is also B into T. So, that means the plastic neutral axis will be here. It must divide the area into two equal parts, right. So, that will be the plastic neutral axis. So, as you can see, the elastic neutral axis has migrated, right. It does not remain at the same location for singly symmetric cross sections. Okay. That is the takeaway. So, now let me do some examples. So, here I have got a doubly symmetric cross section. The question is, determine the elastic section modulus Zd, the plastic section modulus Zp, the shape factor K, the yield moment My, and the plastic moment Mp. For this yield moment and plastic moment, I am saying that take sigma y is equal to 250 MPa. Okay. So, how do we do this? Well, we can do this computation in a tabular manner. Okay. So, what I will do, I will write, let us say this is component, and then I will write this is the moment of inertia of each component about its centroidal axis, right, and the area of that component, and then d the distance from the centroid to the actual centroid of the whole cross section. Okay. So, where is the neutral axis or the plastic neutral axis? It is here, right, and what is the distance? Well, so this is 25 plus 300 by 2, that is 175, and these are all in millimeter, right. Okay. So, I bar A into D, and then we will have to use the parallel axis theorem. So, I will do I bar plus A D square. So, if I do it in a tabular form like this, so let us say first I do it for the flange. Okay. So, I am looking at this flange, let us say, right. So, what is I bar? I bar for this flange, I will write it here, so that I can write down the final number there. I bar is equal to B D cube by 12. So, 200 into 25 cube divided by 12, right. So, that number is equal to 260,416.7. Okay. And what is the area? Area is 200 into 25, that is 5000. And what is the d? D is this distance from this to this. How much is that? 175 minus 12.5, and that is 162.5, right. So, now I have I bar, I have A, I have D square. So, if I compute this, this turns out to be 1.32 into 10 raised to the power 8. Okay. So, then I have got two flanges. For the other flange it is identical, and then I will do it for the flange, the other flange, which is also the same, right, and then I will write for the web. So, for the web, so this is flange and this is web, I bar web, that is B D cube by 12. So, that is 12 into 300 cube divided by 12, okay, and that is 27 into 10 raised to the power 6, okay, and the area is 3600. And what is the d? Well, the d is 0, because the centroid of the wave is matching with the centroid of the whole cross section. So, this quantity becomes 27 into 10 raised to the power 6. So, what I will do, I can now sum it up. Okay. So, this total area which I will need later on 13600, and this is going to be 2.92 into 10 raised to the power 8. Okay. So, this is the moment of inertia of the whole cross section, right. So, this is my I. Okay. Now, what is the elastic section modulus? ZE? ZE is equal to I by Y max. Okay. So, I is 2.92 into 10 raised to the power 8 divided by Y max is 175. So, that will give you 16.66 into 10 raised to the power 5 mm cube. Okay. So, that is my elastic section modulus. I can calculate my now, which is ZE into sigma y. Okay. Sigma y is 250 MPa. So, that is Newton per mm square. This is mmq, you will get in Newton millimeter. If I convert it to kilonewton meter, I will get 416.55 kilonewton meter. So, that is my ZE and my. Okay. So, now I can calculate the plastic section modulus ZP, okay, in two ways. What are the two ways? Well, I can say I consider this area above the neutral axis. I know the cross sectional area of this part, okay, and then I locate the centroid here. So, the centroid of this top part is like this, y 1 bar. Okay. Similarly, here it is going to be identical. So, that is also y 1 bar, right. then I can say ZP is equal to area by 2 into y1 bar plus y1 bar, which is equal to A into y1 bar. This is one way to do it. The other way is I can take each component, I can take let us say this component above the plastic neutral axis, and then I can sum the like this. So, how much is this part? So, that is 150 into thickness is 12 into 150 by 2. So, what I have done? I have considered this, okay, plus the flange, top flange, which is 200 into 25 into the distance is 150 plus 12.5. Okay. So, this is for this one and this one. If I multiply by 2, I get it for the whole cross section, and that turns out to be 18.95 into 10 raised to the power 5 mm cube. Okay. So, what is my shape factor? Shape factor K is equal to ZP by ZE, which turns out to be 1.14. Recall that North American sections, wide flange sections also having similar shape factor. Okay. And what is the plastic moment capacity? MP is equal to ZP into sigma y, which is this into 250 MPa. So, if I convert that into kilonewton after multiplication, 473.75 kilonewton meter. Okay. So, that is the example of a doubly symmetric cross section. Now, let us take a singly symmetric cross section. Okay. So, for the singly symmetric cross section, the calculation is little bit more involved, okay, because we have to locate the elastic neutral axis as well, that means the centroid of the cross section. Okay. So, what I am saying that this Z is my elastic neutral axis, which is at a distance y bar from the extreme top fiber, and this is my plastic neutral axis, which is at a distance y PNA from the extreme top fiber. Okay. So, let me locate the y bar. So, y bar is basically, as we all know, summation A I y I divided by summation A I. Okay. That means, so I have got this one is what 100 into 12 into the distance I am measuring from the top fiber. So, 12 by 2, okay, plus then I have 180 into 10 into what is the CG? Here this is 12 plus half of that. Okay. So, that is 12 plus 180 by 2, okay, divided by the whole area. The whole area happens to be A is equal to 100 into 12 plus 180 into 10, and that is 3000 mm square. Okay. So, this divided by 3000, if you do the calculation, you get 63.6 millimeter. Okay. So, that is y bar, that means let me write it, this one here is equal to 63.6 millimeter, right. Now, we can calculate the moment of inertia I z z again using the parallel axis theorem. Okay. So, what I get for the top flange 100 into, there is only one flange here, BD cube by 12, okay, plus AR square. So, 100 into 12 into the distance square. So, that is 63.6 minus 12 by 2 whole square, right. This is for the top flange plus the web, which is 10 into 180 cube BD cube by 12 plus the 10 into 180 the area into distance square. So, now from here till the middle of this is how much? Is 12 plus 180 by 2, and this is my elastic neutral axis, which is 63.6. So, minus 63.6 whole square. Okay. This is what I get, which is equal to 11.55 into 10 raised to the power 6 mm raised to the power 4, right. So, what is the elastic section modulus? ZE. So, ZE is equal to IZZ divided by Y max, right. So, what is my Y max? Well, if this is 63.6, then how much is this distance? So, this distance is going to be 128.4 millimeter, right. So, Y max is 128.4. So, 11.55 into 10 raised to the power 6 divided by 128.4, right. So, that gives me 89,965.37 millimeter cube. Okay. So, now we have to locate the plastic neutral axis. So, to locate the plastic neutral axis, if you recall, what we can do, we can equate the compression area equal to tension area is equal to the whole area by 2, right. So, I have assumed that my plastic neutral axis is at a distance y p n a from the top fiber. So, then what I can write? I can write 180 plus 12, that means this 12 plus 180 the whole thing minus y p n a minus y p n a. Okay. So, that gives me this much, okay, multiplied by its thickness, that must be equal to the whole area by 2, that is 3000 divided by 2. So, if you solve it, you get y p n a, which is equal to, I got 42 millimeter. As you can see, the neutral axis, elastic neutral axis was 63.6 and plastic neutral axis is at 42. Okay. So, it has moved up, right. So, once this is determined, then I can calculate ZP again in two ways, right. One is calculating the centroid of all the areas and the other one is I can simply say I will consider each area separately. So, AI yi bar. Okay. So, let us say if I take this one first, then what I am getting 100 into 12 into what is the distance from the plastic neutral axis, that is 42 minus 12 by 2, okay, plus then this portion, okay. So, that is 10 into 42 minus 12 into 42 minus 12 divided by 2, right. So, this is A and this is y bar, right, distance from the plastic neutral axis. So, now I am left with this much, right. So, plus how much is that? 10 into 180 plus 12 is the total depth minus 42, okay, and then this multiplied by the same thing divided by 2. So, that gives me 160,200 millimeter cube. Okay. So, the shape factor K is equal to ZP by ZE, which is equal to 1.78. Okay. We can also calculate the plastic moment capacity. MP is equal to ZP into sigma y, which I got 40.05 kilonewton meter, and you can also calculate the My, which is ZE into sigma y. Whatever that number is, you can easily calculate. Okay. So, that completes this example. Now, let me talk about the factors affecting the moment curvature response. Okay. So, as you have seen, for different shape factor, the moment curvature response approaches to the plastic moment at different rate. Okay. So, that means the cross section shape is a factor that governs or that affect your moment curvature response. Then there is residual stresses. How do they affect? We will talk about that. And then there is strain hardening. Okay. What we have assumed elastic perfectly plastic behavior, right? What happens if there is strain hardening? Then there is instability, any kind of buckling, it could be local buckling, it could be lateral torsional buckling and so on. So, how do these factors affect? So, recall from our lecture number 11 that residual stresses in rolled sections are primarily generated due to uneven cooling after hot rolling. The areas that cool fastest, for example, this is I am showing you a isometric view of a wide flange section or I section. So, these areas will be cooling faster after hot rolling. So, they will have compressive stresses indicated by green, and this is a kind of residual stress distribution that people often use. On the other hand, for the web, okay, here in the middle part of the web will cool fastest. So, that will have compressive residual stress, and the other places you will have here you will have tensile residual stresses. So, how does this affect your moment curvature response? Okay. So, let us talk about that, and remember that the residual stresses can be large. Okay. So, now I am taking an I section, right, and this could be your distribution of residual stress, where f is a scalar multiplied by sigma y to indicate or to express this residual stress in terms of the yield strength of the material, right. So, as I have shown you that here you will have compressive residual stresses, right. So, let me write that this is compressive, whereas this here is tensile. Okay. Similarly, here this cools fasted. So, this is compressive and these are tensile. So, this is for the web and this is for the flange using two different patterns, right. Now, before we get into bending moment, let us say this is just a member which I am applying some tensile load or deformation. So, it is a tension member. Then what happens? How does it behave? Okay. So, if I assume elastic perfectly plastic material behavior, and if there is no residual stress, and if I plot the force versus deformation, force versus axial deformation, then how should it behave? Well, it will follow the stress strain response and it will be perfectly elastic, perfectly plastic, right. So, this is how it will happen. Now, the moment you have residual stresses and you are trying to pull it, what will happen? You are applying some tensile force. So, that means this and this will yield earlier, right. So, they will actually depart from the straight line earlier due to the presence of residual stresses. Okay. So, some factor of the Py, from there it will start to depart, but eventually the entire section will become fully plastic when you apply some tensile load. Okay. No matter whether you had compressive or tensile, eventually they will all be tensile stresses when the entire section yields. So, basically your capacity, that means the yield strength of the member as a tension member, is not affected, but the stiffness, as you can see, what is this? This is the measure of the stiffness. So, stiffness is affected, right. So, that means when it is a tension member, no problem. When it is a stub column or a compression member having a small length, then no problem. But the moment it is a column member subjected to compressive force, then the stiffness will come into picture. If you recall that Euler buckling formula, PCR is equal to pi square EI over L square, right. So, what is this term? This is nothing but the flexural rigidity, right. So, if the stiffness of the member reduces, then it will have significant effect on the compressive strength of the member, okay, which we have not discussed in detail, the inelastic buckling of members. Okay. And in the design course, for example, IS 800, how is that taken care of? If you are familiar, I am sure all of you have done the steel design. So, we consider the effect of residual stress and all other imperfections through this factor which is called imperfection factor alpha. That is how we design it, right. Now, consider this member is subjected to pure bending, right, and you have residual stresses as I have shown. Okay. So, here you have compressive and here you have tensile, right. Now, the moment you apply bending moment like this, so what will happen? This part will yield early in compression, whereas here at the bottom in this flange, this portion where you had already tension will yield earlier, right. But eventually if you keep loading it, what will happen? This will reach the plastic moment capacity. So, recall that from before we have studied for the rectangular section, let us say for wide flange section, this is the moment curvature response without residual stress. If you have residual stress, then what will happen? It will depart from the straight line early, because if this is your my up to this point, it is straight when there is no residual stress. If you have residual stress, it will start yielding early. That will be the effect, but eventually it will reach the plastic moment capacity. So, this is what I tried to write here, that this has no impact on MP or on the tensile strength of a member, and this curve that I have shown is valid for axial tension or for a compression member which is stub column. That means the slenderness effect is not coming into picture, and as I said, stiffness reduction will have an impact on the member's deflection and the buckling strength. Okay. So, now here is a very quick example, a simpler one, where this is taken from this book again, Ductile Design of Steel Structure by Professor Brunet et al. So, I am considering an ideal wide flange. Ideal wide flange means thickness is tending to 0, that means this length is tending to infinity, is not it? So, that the entire flange area is lumped here and there is no web, right. And let us say this is the residual stress distribution for the top flange and the same for the bottom flange, right. And let us recall that this is compression, and this is tension here, right. There is no web. Okay. Now, if you for the ideal wide flange, if you look at the moment versus curvature, we know that it is going to follow the elastic perfectly plastic behavior just like the assumed steel material response, right. Now, with this residual stress, if I apply some curvature which is shown here, so this is let us say 0 curvature, then you apply some curvature. So, at the end here the strain is epsilon y by 4. Okay. So, that means you are adding compression 0.25 sigma y. So, you already have 0.75 sigma y compression. So, this will yield and you will get sigma y here, you will get sigma y here. What will happen to the bottom fiber? Well, it is under tension. So, it was 0.75 sigma y, you have added 0.25 sigma y because you have applied a curvature of 0.25 epsilon y. So, this will yield, right. Now, if you keep on loading at 1/4 interval, okay, so this is the first point, right, where the first yielding occurs. So, it starts to depart from the straight line and then you apply another 1/4 of phi y. Okay. So, you can look at this stress distribution at the top and bottom flange, and eventually you see that the entire section is having a rectangular stress distribution, okay, and eventually this curve will reach the plastic moment capacity. Okay. Now, very quickly, what is the effect of strain hardening? So, whatever we have done so far, we assume this behavior, elastic, perfectly plastic, but in reality if we are talking about mild steel, the actual behavior is like this. So, there is strain hardening, right. So, how does it affect the moment curvature response? Well, this is the moment curvature response without strain hardening. If you consider strain hardening, then it will increase like so, okay, and you can do it in open Cs, right. What happens if you have local buckling or lateral torsional buckling of a member? Then the plastic moment you may reach and then drop, or you may not even be able to reach the plastic moment capacity. The member will buckle locally or under lateral torsional buckling, and your moment curvature response can have a premature failure. If you recall, in our Indian code, we classify cross sections into plastic, compact, semi-compact and slender. Why do we do so? Because this cross section are classified depending on their B by T or D by T ratio, and that tells us the plastic section will not undergo any local buckling, and they can give us a behavior, moment curvature behavior or moment rotation behavior like so. Okay. Similarly, compact also, but as you go to semi-compact and slender, then local buckling will take over and you can have premature failure. It will not reach even the plastic moment capacity. Okay. Now, note that whenever I am saying, let us say I am talking about a plastic cross section, so you get like this, but that does that mean that it can go on forever infinitely? No, it cannot go and give you infinite plastic curvature. Then what will happen? Eventually, every member, if it is undergoing plastic deformation, eventually it will fail by local buckling or lateral torsional buckling, which would be inelastic, not elastic local buckling anymore. Okay. So, eventually any one of the two will occur and the member will fail after sufficient plastic deformation. Okay. So, here is an example from a test, again I have taken this from this book by Brunet et al. Okay. So, you can see the top flange is showing some local buckling. Okay. And here I do not see much yielding, there is some yielding here which we are not interested in, okay. But it could also happen after sufficient yielding in the cross section that there is local buckling. Here it is happening earlier. Okay. What is lateral torsional buckling? Well, as I am showing on the right hand side with a cantilever which is clamped here and then some weight is being put at the tip of the cantilever. So, what is happening if I demonstrate with my hand? So, it undergoes, it moves down, deflects and then rotate. So, that is what is called lateral torsional buckling. So, it is deflecting down, bending due to flexor, okay, and then moves laterally and twist. So, that is exactly what is happening here and that is called lateral torsional buckling. I am sure all of you have studied lateral torsional buckling and you have designed members considering LTB depending on their slenderness ratio. So, this figure is coming from a steel design book by Traher. Okay. So, in summary, let us recall what we have done in this particular lecture. We looked at singly symmetric section and we have done some example of calculating the plastic moment capacity, the yield moment, the shape factor, the plastic section modulus and the elastic section modulus. And we have also studied the factors that affect the moment curvature response, right. In the next lecture, what we will do, we will study a procedure to compute the moment curvature response. So, whatever we have done analytically can be done for simpler cross section using EPP behavior, elastic perfectly plastic material behavior. But the moment you want to go for a more accurate representation of stress strain or complicated cross section, then you cannot do it by hand. You have to develop a computational procedure. So, I will talk about that procedure and also do examples in OpenSys. Okay. So, that is all. These are the two references that I have used in this lecture. Thank you and see you in the next lecture.